All right, thank you. And I will try to keep this pace going. I know we're off schedule, but there's, I think, a really good story here. Thanks to Christine.
It's okay if we run long, so you don't have to fight the.
Okay. And thanks to Christine for inviting us. I think this is a story that has not been told previously, and hopefully this is one that will resonate pretty well with the audience here. So I'm from GE Research, which is the hub of the once many GE businesses, now significantly reduced. And okay. Here we go. But the significant remaining businesses power a third of the electrons in the world that flow through devices are generated on GE equipment. Every 2 seconds, the plane takes off with our engines, 16,000 scans a minute on our medical diagnostics equipment. These are consequential products and often require us to have these strategic partnerships with government and other key technology providers. These kinds of products are also part of critical infrastructure. So there are safety factors, they're regulated, they have a long field life and are expensive. So when they are not working, there are significant consequences. So we have employed modeling and simulation for a significant amount of time. It is very important, of course, though, that these not be garbage in, garbage out kinds of models because of the long life, the high consequence, and the critical infrastructure of them. So I'll talk through kind of how we got to where we are. And we mentioned that there's one of the ALCC awards that'll be using Frontier is on one of our projects. And I follow these 3 phases to understand, to predict.
Can you go to your second screen and scroll over and close the black bar on that?
All right. So when I say to see, I'm talking about using the computational model as a scientific instrument itself, the same way we'd use a microscope or a telescope or what I call a hyperscope here to look at massive dimensionality in ways that our own perception is inadequate. And our studies and progress have mainly been in the swim lane of computational fluid dynamics, which apply to many of, in fact, kind of all, one way or another, of our remaining products, whether it's jet engines, power plants, so it's a gas turbine, hydroelectric, wind, and such. There's a high interest in understanding turbulence and its effects in the operation of that equipment. Specific to aircraft engines, we have a program that you see on the right here called RISE. I'll talk more about that. That is the successor to 2 very successful engine models. The first on the left there, introduced in 1979, was one of the most used engines in the world, and the LEAP replaced it in 2016, reducing fuel burn 15% from the prior, and we have some very aggressive goals with RISE. Now, one of the important aspects of this to understand is this is seen as a path to hydrogen. And hydrogen has been one of the priorities that the Department of Energy has declared. But to get the benefit of the zero carbon emissions out of hydrogen as a fuel, there are things you need to address. Right now, in how far you can travel at a given price, hydrogen is significantly more expensive than jet fuel. To get the same number of joules out of it would require 4 times the volume of storage of the fuel. So that's going to impact how many passengers you can carry. And then similarly, the range of the aircraft. So in order to make hydrogen viable, we have to improve the propulsive efficiency significantly. And you can see the diagrams there. We're used to seeing the nacelles on our large aircraft today, which contain the jet engine. The design that we're pursuing for propulsive efficiency is the open fan, which is the one that's shown to the left in each of those diagrams. So remember this because we're going to come back to it. Now, at any given time, we've only been able to simulate a problem as large as will fit on a given system. So at the beginning, we could only look at one blade at a time, expanded it to multiple blades. And really what we care about in terms of the airflow is not the blade, but the passage between 2 blades where the air actually goes. So then we scale up to multi-row and full stages of the engine. We've historically used symmetry, like a 1/8 cut of the full wheel, then going to full annulus, which is the entire circumference. And then the dream would be to do a full engine end-to-end full annulus. Back in the mid-2000s, we had done this projection. The scale on the x-axis here is exponential of what it would take to perform certain kinds of simulations at first switching from 2D to 3D, then up to an unsteady analysis, which I'll talk about in a bit, and then going, the blues are blade only, green is staged, like an entire stage, and then the red would be multi-stage, and pushing out to like 2026, we're looking at the most aggressive of these. But at the time, we didn't know what the path would be to be able to do these kinds of simulations. Now, the group that I was leading at the time was doing embedded systems. And so we were familiar with FPGAs, and we actually had done some CFD kernel implementation in FPGA in the 2002 to 2004 timeframe. There were significant increases in performance that we could get from GPUs. And then the PlayStation 3 was out, and we had the potential of looking at the cell processor. Now, GE may have been fortunate in that our group had experience in doing high integrity embedded computing, like the core compute system for aviation, onboard satellite systems and such. So we were using FPGAs for that platform, and we're quite comfortable implementing those, although the process chain was significant. Because of image reconstruction in healthcare, we were familiar with using GPU acceleration. And we were actually early in on the STI cell. This article in IBM publication talks about some great performance that we got for it in doing an MRI algorithm implemented in the cell processor. So before 2010, we were already kind of pre-ready for this use of accelerators to get performance, but we had only looked at these in embedded or single workstation kind of scenarios. Our x86 clusters were modest, and it was in the high reliability architectures like the Blue Gene, there was a perception that it would be very difficult to port to them, but we got some assistance from Jim Sexton's team at TJ Watson. And I think our port of Tacoma, our RAN solver, took a day. And so that put that to rest. And we were running on the Blue Gene L in Rochester, and then some of the performance improvements started. So let's go back to the engine here. So the last part of the engine called the low pressure turbine is where we capture all the energy that's being generated upstream. And if we can choose a design that maintains attached flow as shown toward the top, we get high efficiency, whereas turbulence, as seen in the red, and separated flow, we lose efficiency in the design. And so we run simulations where we want to see if the shapes and other factors that we've selected are creating these kinds of flows. And so we wanted to run a jugular experiment on this to see if there was anything useful running unsteady computations instead of the steady, which you can see up at the top, which is a time averaged view of what's going on in that stage. So we took this to Oak Ridge, and on Jaguar, we ran an unsteady analysis, and you can just see by comparison the top and the bottom. What we have here is there's a strut, and behind that strut is this wake that we thought there's thousands of RPMs going on. That's just going to blow apart the wake from that strut. Not true. And this, again, for symmetry, you can see that, in fact, with the unsteady analysis, we could see that the strut was impacting things, and we could identify areas of separated flow. And because the initial row is a stator, not a rotor, meaning it is always behind the strut, there were actually design decisions that we could make to compensate for this. So this was seeing something that we couldn't see before. So imagine you can use the top half of the slide to design, or you can use the bottom half of the slide, which is more informative here. And this has even gotten more pronounced as we have expanded the scale. So in 2011, we acquired a Cray to be able to do proprietary problems on this. Another early end project that was very enlightening, this one done on Mira at Argonne, was in exhaust noise prediction. This was some of the first work that was reproducing physical test data predictively. And this leveraged a code out of the Air Force. So as far as Exascale, this is a panel in 2011. It was in the basement of the Capitol where I was representing industry, and we didn't really have an Exascale problem at that time. So I'm thinking, what can I actually say? So I changed it to the pursuit of Exascale, and how important the pursuit would be in impacting things where, you know, when just as petascale would commoditize terascale and make it affordable so everybody can do terascale stuff, Exascale would do the same with petascale. But I did add a Exascale-sized problem, but this was completely infeasible to generate at the time. And the barriers in creating industrially relevant problems in terms of the mesh size and detail and validation and such are still an obstacle, and something that I've reached out to several labs to discuss how to address. And I think it's a problem worth more attention. Another early success story, unfortunately it's a negative success, is in looking at the nucleation or the formation of ice and water droplets. And the interest here was in terms of ice adhesion to things like wind turbine blades, aircraft engines, even subsea oil exploration contexts. And strangely enough, how this actually works mechanically, even though this is something we see all the time, is not deeply understood. And so this was one of the largest scale simulations in the world at the time, and it did give insight. Unfortunately, it was insight that the countermeasures that we were looking at to reduce adhesion would not work. But it allowed us to, create a lot of interest and excitement around the ability to see this and then redirect our resources elsewhere. And in fact, that story is in the case study that Masako Yamada wrote in conjunction with kind of the brief history, which is about up to this point, that we put into this book that came out in 2015. So this is kind of the glory slide. So over the years, we've had a number of projects at various labs that have touched on many of the different components within the engine. This was an earlier version of this, appeared at National Lab Day on a live screen. And I think it's a great visualization showing the partnerships and just the power of what you can see. So shifting from see to understanding. The story that I would next share is around gas turbines. So this is big. This is 500 tons, 39 feet long, 16 feet in diameter, 100,000 parts. We are the largest supplier of gas turbines in the world. And so efficiency on these is of significant impact. And along the way, you also want to reduce emissions, carbon dioxide, NOx, and to a degree noise. Noise will come into the story here. So while a gas turbine only plant is about 33 to 44% efficient when you do what they call a combined cycle, where you capture the heat and you then turn that into a steam turbine, which acts in conjunction. You can push that into the mid 60% range, which for a machine is an incredible efficiency rating. So the each percent of efficiency translates to 17,000 metric tons of carbon dioxide, or about 3,500 automobiles. And the US combined cycle fleet is about 200 gigawatts. So 1% on that is about 3.5 metric tons of carbon dioxide. So this is a single point with dramatic potential impact. So a great story here is one that was told by Joe Citino from our gas turbine team and the keynote in the 2018 Smoky Mountains conference, where he shared the story of outreach to the national labs toward a predictive model that would have sufficient scale and capability to simulate the system of interest. The problem was, before having access to these machines, we could only look at one combustor at a time. But there was an interaction between multiple combustors that was creating some problems in the design that we would only be able to see once we were able to simulate multiple combustors. And so we received assistance from the labs, and you can see in this diagram, at least that they look different, not being a mechanical engineer, from the unstable to stable. The design change was moving one hole, a fuel hole, by 0.1 inch. So, but having the ability to see this and understand the impact is a key part of the value that comes out of this. So we had started to build this portfolio of these great projects with impact. And I definitely would say Susie and David in the back of the room were key partners in having us engaged in making parts of this happen. So now bought in, we started expanding these partnerships. This was looking at wind farm scale simulations to start to get an inkling of the effects of wakes downstream, and we're going to come back to that. We had additive manufacturing, which was becoming more prevalent. So, you take metal powder and a laser that will melt it, add powder, next layer, next layer, next layer. And this became so critical to our aircraft engine business that we actually bought the 3D printing companies there on the left, Concept Laser and Arcam. And so now we're in the metal 3D printer business as well, with ourselves as our primary customer, but with others as well. So understanding materials and the grain structures in the process, and we've leveraged the HPC for Manufacturing program in looking at this. So by 2017, in peer-reviewed competitive grants, GE had already used over 1 billion core hours on the National Lab machines across a number of the labs. And by today, that's 14 Insight Awards, 22 ALCC Awards, 6 HPC for Manufacturing, and other directors' discretionary grants, et cetera. But we recognized all through this the obligations that we had also to give back and to keep pace with things like the Insight scalability requirements. In 2019, at the Exascale annual meeting, I put together the poster on the left, and this is just kind of zoomed in for more this shape of some of the aspirations that we had for Exascale, including multi-scale wind turbine actions, the inlet distortion flow. So this is where you have aggressive crosswinds to the flow. So it's not like a uniform, I'm flying, into a headwind sort of thing. And multi-scale material modeling. But this one here, this remains a big challenge, which is combining, once again, I talked about modeling just the combustor or just one combustor, linking the simulation of the combustor with the simulation of the turbine that follows it. They have different geometries that they have to hand off, as well as different physics that are of interest. And so today, those are boundary conditions as a handoff rather than a coupled simulation, but it's pretty intuitive that there are insights when we can actually combine these. So getting to the recent awards that we've received, this ALCC award, and this did have an update, so it was renewed, was looking at the impact of coastal low-level jets. So in the natural thermal cycles of the heating of water versus the heating cooling of land, along the coast, there are these jets that have a distinct non-monotonic velocity profile that will hit the wind turbines. And it's not an effect that is universally seen, but it is prevalent in the East Coast of the United States. So in the New York Bight installation that was going up, we wanted to understand these effects so that we could predict what the performance of the wind turbine farm would be, and understand the reliability of the operation and such. So that's one aspect of this. The other is in terms of the wakes now. Believe it or not, the wake effects downstream can span over multiple kilometers and can reduce the efficiency of a downstream wind turbine up to 40%, and also potentially increase the out-of-plane loads on the turbine of up to 40%. And so a lot of the design is idealized turbulence, not realistic based environmental conditions. And there is no wind tunnel that you can put a wind turbine in to do this. So this is the only way of being able to see these sorts of things. So feasible at petascale. We have the atmospheric turbulence, the impact of weather on the turbines, turbine-turbine interactions at order 10, so basically a single farm, but still not able to do things like complex interactions with wave swells and more complicated atmospheric phenomena, and then interactions between wind farms, which just put a pin in that for a second. So switching to the to predict phase here. So we're at this current status in the diagram with these infeasible solutions. But with Exascale, we believe that the wind farm interactions become feasible. So here, these are two wind farms in the Baltic Sea that are tens of kilometers away from each other, and the wake from one farm will impact the profile incoming of the other farm. And this greatly increases because of the number of turbines that are participating, but also the overall scale of the problem. It may also open up some of these other atmospheric conditions. The second ALCC program was trying to understand some of the flow physics that impact engine design and are relevant to the other stuff we'll talk about. So going from a laminar smooth flow to a turbulent flow, which would reduce our ability to capture the energy, reduce performance, and potentially create what they call flutter, which is a noise. It's like a standing wave in the system. We needed to look at how far up do we push what's called a Reynolds number. The Reynolds number is a function of viscosity in how you're modeling the fluids. And especially if we were going to employ the results of these simulations as a training set for surrogate models, we needed to know if we were extending this into the sufficient region of sufficient fidelity to encompass these kinds of effects. So this study was just looking at what are those tipping points in terms of the sensitivity on that, and this is in the high pressure turbine. So this builds to our current program. And again, going back to the beginning, this RISE demonstrator, and so this is the joint venture. CFM is a 50-50 operation between Safran in France and GE. RISE stands for Revolutionary Innovation for Sustainable Engines. It is the path to hydrogen, but also other things. It's the open fan design as opposed to the nacelle, as mentioned before. And this is something that is probably not well known. So before we can run a flight test, we run a rig test. This is typically done in a wind tunnel, but these wind tunnels are smaller than the actual product. And this is how big a difference that is. Now, So we build this tiny version that will fit into NASA's wind tunnel. And the relevant Reynolds numbers for the airflow of the small engine are significantly lower when compared to the fans that you see in the full product. So there is no wind tunnel that we can use to test the design at the product scale. So that is not tested until the flight test. And we have to try to sell these things. So we need to at least bracket what its performance will be post-certification when we haven't even done a flight test and such. So we laid some foundation for this with the 2021 Insight, and this completed the first of a kind, well-resolved large eddy simulations of the full 3D open fan at high Reynolds number. And this was still at rig test scale. And if we wanted to run these at, and cruise is significantly simpler because it's more steady than takeoff conditions, which have a lot of dynamics to them. So if we wanted to perform these same kinds of simulations at the flight scale, we would need a much bigger machine. And this is where we approached Oak Ridge and ultimately put into the ALCC program on this proposal to leverage basically everything we could possibly get access to. And so the ALCC award was on Frontier and Summit and Perlmutter. And you can bet that if anybody leaves spare hours available, we will be eagerly seeking to scoop those up. So just as a comparison, to run the takeoff test at the rig test scale, that simulation would be about 70,000 node hours on Summit. That same simulation at product scale, so the flight scale, is over 6 million node hours on Summit. So we love Frontier. The other potential approach for being able to greater leverage value out of this is thinking about the ability to save the results of high fidelity simulations as storage has become affordable and abundant, rather than doing an optimization where we're just throwing out things that don't meet our objective criteria. Can keep those results because maybe our objective criteria are wrong, and employ that as a data repository for machine learning for surrogate models. However, that repository needs to be very concise in where it is relevant to use. And if it is insufficient for the problem of interest, you can run some more high fidelity simulations, expand it, retrain, and employ the new technique. Now the payoff is significant, and the examples here, left to right, you're supposed to imagine that they're identical, right? And they are, and it only has to be good enough to make a decision. It doesn't have to be exact, but enough to provide enough confidence for decision making. So as particularly on the right here, you're seeing an example of where one solution takes 2 days to compute, and the one on the far right is able to run 1 million solutions in 15 minutes through a surrogate model within the constraints of that problem. So having a workflow that allows you to assess the question that you want to ask, determine if you have a sufficient model to do so. If there is a gap, identify the missing high fidelity or test data you need to add to the repository, create a new surrogate, and then use that to answer your question, and maybe just that one time. This is why I call it a bespoke surrogate model. And the efficiency of that process being the factory part, this is potentially a novel way of doing engineering, and it's part of the paper that just last night we found out was accepted to Smoky Mountains. So we'll be presenting more on that there. And speaking of that, along the way, one of our obligations is publication. So out of the awards that we've made, and you can see some of the institutions on the top, there have been many white papers that have come out of it. In the recent awards, this is a list of those publications. And again, the understanding the obligations and what's at stake, and how to make sure that you guys are getting the support and the messaging you need. There is this track record all through of GE having a sustained and consistent support and shared vision with the Department of Energy in the pursuit of Exascale, and now Exascale, and the value of leadership computing facilities, but also the talent at the computing facilities and the ecosystem that has been built around those. We do want to say thank you for all of that. The flow has really been looking at the DOE being out in front. I usually say paving the road of understanding and bringing into feasibility the state-of-the-art hardware, which we can then select from to tune to our particular needs. Us doing feasibility studies that are out there still in the low TRL science realm, where internally we will then take it and do validation and production, proprietary kinds of workloads, building out the scalable libraries and software applications that we can adapt, if not adopt, and apply internally. So the GE tagline for now is building a world that works. These are, serious, life consequential, critical infrastructure kinds of products, regulated, and so that presents obstacles that maybe others do not have, but it is the guiding central vision of the company. We are, as you probably heard in the news, splitting into 3 companies, and every indication I have is that GE Research is still going to remain a central research facility to those 3 companies going forward. But that's a story that I do not think has been really told in that fullness previously. And once again, thank you.